Hello, we are Team 22011 and we will be presenting our project Wearable Pulsed Electromagnetic Field Sensor for Clinical Trials Compliance Applications, sponsored by Regenesis Biomedical.
Hi, now we're going to introduce our team from left to right. My name's Anna Karen Romero and I'm a biomedical engineer.
Hi, my name is Sam Schultz and I'm an electrical and computer engineer.
Hi, I'm Sarah Bierman and I'm an electrical and computer engineer.
Hi, I'm Jess Graham and I'm a biosystems engineer.
Hello, my name is Nasral Jamaz and I'm the industrial engineer.
Here's our design day poster. If you would like to pause and read through it, go ahead. But we're going to go ahead and talk about every component. We're going to start by going through the introduction and background.
Patient noncompliance can cost a clinical trial a significant amount of money, time, and resources. Regenesis Biomedical has an FDA-approved treatment device to be used in clinical trials. This treatment uses pulsed electromagnetic fields and is administered to the patient via a treatment pad. The patient must make physical contact with the device for it to be administered. They have asked us to make a wearable device that senses their treatment to monitor and increase patient compliance. Our wearable device will detect the treatment and notify the user of the treatment status via a mobile application.
Here are the functional requirements for this project, and I will be highlighting a few of them. Number 1, the system shall detect the presence or occurrence of a PEMF therapy session within the treatment area. Number 2, the PEMF sensor shall be wearable by the user for at least 24 hours. Number 3, the PEMF sensor shall connect to a host and transfer information bidirectionally via Bluetooth. Number 6, the wearable PEMF sensor shall be able to be used outside the clinical environment. Number 7, all user-accessible surfaces of the PEMF sensor shall be biocompatible. This is the system block diagram for our project. The system block diagram maps out how the system will function and the placement of each component. The central component of the system block diagram is the microcontroller, which is connected to the power supply, PEMF sensor, and Bluetooth radio. All of these components are housed by a 3D printed housing and is attached to the wrist using our wrist strap. The PEMF sensor will be connected to the PEMF device and the iOS application to display treatment information. The system architecture for this project includes the 6 assemblies that work together to detect and display PEMF treatment compliance. These include the power supply, PEMF sensor, microcontroller, Bluetooth radio, iOS application, and device housing.
First, we're going to start off looking at the PCB design for our board and looking at the schematic for it. The printed circuit board for this device uses an antenna loop to pick up the electromagnetic field pulses from the treatment sensor. The current then goes through rectifying diodes into a comparative circuit using op-amps that will let the signal go to the microcontroller as long as it's at the right voltage. The microcontroller is an ESP32 chip with a Bluetooth module and an RF antenna integrated into it. The PCB also uses a battery and a voltage regulator to ensure the voltage is 3.3 volts throughout the board. There's also pads to attach a programmer to upload the code to the microcontroller for connecting the app. This is the final routing of the board. This is our finished PCB with everything integrated on it, including the microcontroller.
We decided to use a 3D printer to prototype our electronics housing and used polylactic acid or PLA to print this housing. We came up with a design that is similar to a watch face, with rounded corners to prevent wearer injury, as is one of our requirements. Our final PCB was 7 by 3.8 centimeters, and the watch housing is 8.6 by 5.5 centimeters, which met our sponsor requirements for something small and wearable. This is our third version of the device housing, as we had to make it large enough to hold the PCB and fully insulate it. The watch face detaches from the watch bottom, which is large enough to hold the PCB. The watch strap goes through the watch face and is made of Velcro, so that the wearer can easily put it on and take it off. And additionally, the wearer can adjust the Velcro depending on the size of their arm. Both PLA and the Velcro strap are biocompatible, so that there should be no injury or irritation to the wearer's skin, and the integrated parts are comfortable for the patient to wear.
In order to monitor the patient's treatment status, we needed an interface for the user to interact with. To do this, we developed a mobile application using Swift UI on Xcode on a MacBook Pro. One of the requirements for the app was to be password protected. We set up a Firebase account to store the user-created usernames and passwords to satisfy this software requirement.
First, a user goes to the Create Account page and creates a username and password for their account as shown in the video. After they create this account, they will then be immediately directed to the user homepage where they can monitor their treatment. If the user then signs out, they can go to the sign-in page and use their account that was just created. This demonstrates that the account information is properly stored in the database and the user can successfully log in. Now we will walk through our testing of the PCB that was done at the Regenesis laboratory. As you can see in the video, Sarah is switching between contacting the treatment device with her left hand. When she is receiving treatment in her left hand with the PCB placed on her right wrist, you can see continuous pulses of treatment on the oscilloscope being detected by the circuit. When she then takes her hand off the treatment device, these pulses are no longer being detected on the oscilloscope. These pulses being seen while receiving treatment verify that our circuit can successfully detect when a patient is receiving treatment in clinical trials and when they have stopped.
The same treatment detection is seen in different body parts. Here, the person is putting the treatment on his knees and the PCB is still detecting the treatment. It's important that our device is able to detect treatment in different areas because patients are treating chronic pain in different parts of the body.
Now we would like to go over the lessons that our team has learned throughout the past year while working on our project. One of the main things that we learned in our project was to document everything. In the course, there were many deliverables due at a time, and we found it very important to document at all stages of the project, including the beginning, middle, and end. Our team would start each lecture by creating a shared notes page so that the team could collaboratively take notes and document the lecture content to make sure that our deliverables did not have any inconsistencies. Through this project, we also learned how to communicate effectively as a team. We set our expectations early in the team charter and continued to set weekly expectations of what the group hoped to accomplish. This helped our team stay on the same page when it came to creating documents, and we were able to communicate to each other exactly what needed to be done each week. The final lesson we learned was how valuable respect is as a team. It helped our team morale stay high and created an inviting learning space that we all wanted to be a part of. This is a table listing out the deliverables that we will be returning to our sponsor at the end of the semester. We will be providing them with PDFs of our final report, as well as the customer satisfaction report for them to fill out at the end of the semester. Additionally, we will be delivering all of the prototype components to our sponsor in each of the 3 categories consisting of housing, PCB, and software. The main deliverable will be for our final PCB with all of the components and CAD files along with it. We will also be providing them with the source code for our iOS application and the STL files of the device housing.
Team 22011 thanks you for your time in watching this video.